So Eric's going to start out here.
Thank you very much. Well, you might remember last year, those of you who were in Aerospace Corporation, where Peter got to make a fine presentation on his novel hypothetical Mach field detector. And it was met with a healthy dose of skepticism, right, which is always good, right, Professor? As well as a bit of enthusiasm, but lots of advice. So we wanted to get back and report to you some of the changes we made to the device vis-a-vis the suggestions you made. Martin suggested to make sure the battery failure was not the obvious issue, to use light bulbs in series, and Peter will address that in a few moments. Jose introduced us to some really interesting people and turned us on to the book by Maurice Allais, Should the Laws of Gravitation Be Reconsidered? And you can't really have a discussion about the Mach field without discussing gravitation, because obviously they're intertwined. So this, you might also recall, came about when Peter was doing some experiments when he was a PhD candidate at Cambridge University. And in his original iteration of this device, much more simple, he actually noticed a transient mass fluctuation. Of course, that was the hook, and ever since then he's been hooked by this and looking for this continually, and then he met Professor Woodward, and from there he's continued to grow, and now the device has gone through 2 or 3 iterations and changes and such, and thanks to you, we've added a few things, and we have more to add. For example, Tony suggested that we change the sensors, the batteries, and change them, where's Tony, with capacitors. And that's, I think, yet to be done. Another suggestion was to use more sensitive batteries and get away from the NiCad batteries, because between the draining and the sensing, we had a lot of problems with it. Also, go to a real-time sensor so we can get real-time data and therefore better and quicker feedback. So these things are being slowly incorporated into the device, but remember, time is limited as the resources have been. Peter, after all, is a university professor and therefore not terribly well paid. So still some exciting things coming, I think, and we talked about this at lunch today. Why do we all do these things? Why do you amazing minds and people do what you do? Because of your fascination for the unknown and trying to discover what is yet to be discovered. And so what we do with a device like this, which is rather simplistic, considering all the wonderful presentations that have been made so far this week. But who knows? If there's something that you can divine from a detection device, whether it's truly a Mach field detection device, Martin, or not, that remains to be seen. But if there's something we can learn from the peripheral occurrences, then why not? We heard twice, just in the last 48 hours, I think from Professor Woodward and Heidi, that 2 of their changes were serendipitous. It isn't so much science from serendipitous changes and things just being offered. Yes, sir?
Cold luck.
Yes, sir. Cold luck. So with that, I'd like Peter to do a brief run through on what we've been doing so far and go from there.
Thank you very much. If you got a chance to take a look at our abstract, we are talking about these modifications that we've made to the system. There are about 4 people in here who may not have heard the talk last time, so I will not only go back and talk a little bit about the experiments that we had just done before the second Advanced Propulsion Workshop, because I want to make sure everybody's in the same sort of place. But again, what we found was that we're seeing that even when other people get involved, we had 2 undergraduate students this summer, actually trying to run experiments, and I'm very excited to share their report about halfway through here. I'll get to that. But the main aims of this talk is to discuss these recent empirical review things that we've come up with, and also give you some of the details, the updates that Eric just mentioned, and talk again about these ideas of these statistical outliers, because the things that have been most intriguing to us is why do certain batteries have these anomalous deviations that always seem to be pointing towards one of these major alignments of a near mass. And again, the most important thing, which Eric reiterated at the beginning, which is why we show it here, is because we believe with the open minds that you have and the creative thinking that you have and your great knowledge, you can help steer us down the path I think you've already done. When we get to the end of this, and I show you just a couple summary slides of what's just been happening this summer, I think you'll realize that the comments that we were able to take on board already indicate that we have a sensitivity now that suggests that this thing might actually be real, as opposed to just something that was totally by chance. So oftentimes you hear people say, well, our next steps are, and then they always go off and do something different. But in the case of us, this is what we told you our next steps were last time we saw you. And in fact, it's exactly what we did in terms of actually reviewing all of our previous experimental data, which I'll show you a few statistics from that. We did build a new real-time sensor array communication connection so that we could look at this stuff in more real time, maybe give us some insight into why batteries were having these sort of anomalous deviations. We did complete the submission of a full patent. That's still in process, and we are beginning this and continuing and ongoing this collaborations with other institutions and partners and submitting our results for review. So I had a very, very long laundry list after meeting with this group last year, and then the groups over in Europe that I spoke with about it. And then we tried to, as a team, try to prioritize high, medium, and low modifications. And these were the high. We already mentioned the batteries in real time, looking at the old data, gathering mass gravity data for near masses, and looking at the over-under views of the Earth from sky maps, and randomizing and reversing our measurement protocol. And again, all the things that you see that are here in green have either been completed or are ongoing and have begun. We still haven't gotten to the point. Some people said it was very easy, just change out your lithium ions, but we will do that. It's just a matter of, we've only run another 30 or 40 experiments since we saw you last time. So again, this is the device. I'm not going to spend a lot of time on it. It has a central inertial wheel. It has two motors that pretty much drive that inertial wheel up to 6,000 or 7,000 RPM. And then it has 8 arms that have 6 batteries on it. The sensors now are actually the batteries that are being monitored in terms of their voltage dissipation over time. This is our I'm only showing this old data because this is what got us pretty interested in this. We ran controls where we didn't actually try to torque that that internal inertial wheel, and we got a certain distribution of voltage departures after the fact. And then we would do what we were calling experimental runs at the time, where we would look at the distribution of the voltage of the batteries before and after. And we saw some things which we'll come back to at the very end of this when I compare these, what we thought were control experiments and experimental experiments, with what TU Dresden actually suggested. Martin suggested, well, why don't you run batteries? Why don't you just run lamps off your batteries? Because really, if there is anything that has anything to do with that inertial wheel, just using lamps instead of an inertial wheel will show you something. And I think it did show us something, but I'll leave that for you to decide when we get there. But the thing that really got us on the path of this, which we showed before, was first of all 2 battery polarity reversals that I got in my laboratory at Cambridge, which happened instantaneously, and that was a long time ago. But then back in 2016, when we got these very, very, very large outliers for 3 different experiments. And that, again, thinking about the criticism that we got, that this is battery failure, we would have probably just dismissed it at that as well, had those battery failures not been tracking not only the setting sun, but the setting sun was in alignment with the moon and the Virgo supercluster, and so there was an awful lot of predominance of near mass that was actually sort of moving, actually as the Earth rotated, that the different battery sort of seemed like it was pointing to. And it was like, that was very odd. If it was 1, you could write it off. If it was the second one, well, maybe you could write that off too. But when you get 3 in a row, now we had 5 very anomalous reactions of these batteries, and we're saying, like, well, what's going on? Is there a possibility that there's some sort of connection here? And again, I mentioned this only because if you look at our sigmas, LIGO is very, very critical and really important. That was a 5 sigma outlier, and whichever convinced everybody that we'd found the gravitational wave, right? That's 5 sigma. And so, again, this is how our thinking thought changed over time. And if you are going to be a scientist, come up against dead ends, you come up against criticism, you take that on board and you change your direction. And our direction has changed quite a bit. First of all, we thought, since we had originally had battery polarity reversal, that we were going to see it over again and again. And of course, we ran dozens and dozens of experiments and didn't see it again and again and again. And so we were always looking for that in one direction. And then we said, if there are these impacts, they were going to, are they going to actually affect the batteries physically? Is it actually something that's coming into the inertial wheel and it's just going to physically alter the chemistry of the battery? So we made that Death Star thing that we showed you last time, where we just covered the whole sphere with batteries everywhere. And that turned out to be a dead end, because it only seemed to be that the batteries that were impacted were the ones that were under heavy drain, maybe a 1 amp drain or a 1.5 amp drain. So obviously it had some electromagnetic connection between the batteries and the current that was running through them. And again, I told you that this is probably our biggest thing that we just shared with you last year, was that the sky became very important. Like, what was in the sky? Why did that become important? Because before we just figured, well, the Mach field is everywhere. You know, it's ubiquitous and it's uniform if you go far out, and the universe is infinite. Therefore, why should we care what's in the local sky? Okay, but we're following this now, and hopefully you'll see when I get done in this little part why that's even become more important. So we revised and improved our protocol, because prior to that we were measuring batteries and basically putting them in and run the experiment expecting something great to happen. And when something great didn't happen, except those few outliers that you saw, we said we better be checking the battery voltage for every battery before and after. So that was our first jump forward. Let's go and be a little more scientific about it. And then we would always read the voltage in and out of the batteries and calculate the delta V. That was the big change for that too. And the way that this little detector works, it's this sphere, it's about that big. It's got 8 arms on it. And there's 6 batteries that are actually the sensors in the middle part of the arm around the inertial wheel sensor. And then you hang it onto an array. And then basically we obviously keep track of where they all are and rotate this thing through. The thing gets rotated for different experiments so that A is not always up and E is not always down or what. So in 2017, we moved to that, of looking at each battery individually, carefully looking at the sky maps, and actually going back in time and saying, were there any big things in the sky? Because we had thought we'd seen that following and tracking the sky, and our Cambridge experiment said that there was a big alignment in Virgo above. And so we said, let's take a look at the upcoming lunar eclipse, solar lunar eclipse, and the alignments in last year, right, which we spoke to you. And I'll show you some of the data from that, only because at the time we had just produced that data and I hadn't had a chance to totally screen it a third, fourth time, but we've done all that now. So just very quickly, first experiment of the eclipse, when the eclipse is going by, that's about where our laboratory is. We were at about 75% of the eclipse zone. We began experiment run right here when the sun and the moon were directly overhead. And based on that, we basically had some very strange occurrence on our echo arm, where the one battery went really, really high and other batteries went really, really low, and everything else was left in the middle. Then experiment began at 239 because it takes a lot of time to read and measure all those batteries and then put a new set in and get ready to go again. And then here we go. It was much closer to the hotel arm. Over the battery.
How many batteries do you have on the unit?
There are 48 batteries. 48. There's 8 arms, 6 batteries operating every time. Yeah, so there's all the way around those 8 arms. So, and then this one actually looks normal. And so we thought, like, well, maybe there's nothing actually happening as dramatic as here, but we thought this was quite significant. But if you looked at the hotel arm, all of a sudden you realize that the highest and lowest battery were actually at the perimeters of that, which sort of got us starting to think that maybe this idea of the high and low battery and the high and low arm as a pointer might actually be something that we should consider. Because if there is something electromagnetically interacting with that wheel that we have no idea exactly how it works or how it, maybe we'll just look at each arm and look at each battery individually and say, is it telling us anything? And so we were very interested in 2017, which is what I presented to you last year, 18th, 19th, 20th, and 21st, when we were getting this big alignment of local or near matter between the sun and the moon in the Virgo supercluster. You can see there's also Mercury, Venus, and Mars very close in there as well. But we set this setup here. It's not very scientific, I know, based on all the wonderful studies I've seen everywhere else. This is my living room. We took it out of the basement. We brought it up in the living room. We don't even know if that actually made it not as good. But anyway, we brought it to the ground floor of the house and we set it up so that it was facing the southern horizon and basically could tilt it at the tilt angle. And then I'm not going to go through the measurement protocol. This is all in my presentation from last year. But basically, all of these experiments, we've run the batteries basically 4 minutes, powering the internal gyro motors after the gyro has already been brought up to speed by external power. So that's basically and then we post-process the data. So this was very interesting. Last year, I basically said, in this yellow area, I said there was no targets. So instead of saying 100%, 100%, 100%, I was saying 100%, 100% hits, and then I was saying like 87 or whatever. But what was very interesting is after we met, then I saw this NOVA special about the black holes in the center of all the major galaxies, and how we've been learning that most galaxy formation includes a massive, supermassive black hole in the center. And so I said to my guys, I said, well, where was that supermassive black hole? And where was it on the day of these experiments, in the supermassive black hole? And it turns out that the Milky Way hits were pointing right to that supermassive black hole. Again, another coincidence? Very possibly. I mean, you remember my whole presentation of this is coincidence upon coincidence upon coincidence, until finally, maybe you actually have something that may be real, and you should be looking at it a little more closely. So again, 100% of all of our runs during this short 8 experiments over this one day when we had what I call the prominence of this alignment astronomically, 100% of those runs had Earth as a target mass of one of the interactions. 63% of them had either the Virgo sun or moon, or some combination of them also as the target. So average 2.5 interactions per run, one interaction per run for the Virgo sun moon. And so this was, what do these things mean? Is it a coincidence, or could it possibly be real? What I found very interesting is when I was looking at the Earth results, they all seemed to cluster around whatever was the center arm that was facing down into the Earth, and you got this sort of little distribution around it. Is that, to me, when things are random, they appear random. When things start to become a pattern, you start to say, well, is there a pattern here? Is nature trying to teach us something or show us something? And of course, going out here with these interactions, all the other interactions seem to have one of these major targets as a way to do it. And what was interesting is the day before, you could almost see this prominence of mass building, because only 70% of the interactions had hits, and on the days after, it was about 69% for the 2 days after. So it was almost like this prominence built during that day, and then just like any other kind of solar eclipse or astronomical alignment, it was like it was actually moving in a natural kind of way, and it's all of a sudden it's like, could this be real? I mean, I don't want to be kidding myself, but could it be real? So I'm just going to run through a couple of these. Again, we used to think these were control experiments. A control experiment meant we didn't rotate. We rotated the internal mass, but then we didn't torque it, thinking that if you torqued it, you'd get the universe to give you more of a response, because Mach's effect would say you want to keep this thing the way it is, and if you try to torque it, that means you're providing a force. There's got to be potentially a reaction force, even though we wouldn't know what it was. And lo and behold, this happens on that control run. And then here we have outliers again on another one. And I'm not going to keep reiterating the fact that when I show you these outliers, each one of these outliers is pointing to one of these significant prominences. Okay, so that's already assumed. I'm telling you that. So Foxtrot was pointing right to the Earth here, and Echo and Foxtrot, Bravo was unaccounted there. But so on October 21st here, so Bravo in this case was actually pointing to the, because I didn't get a chance to update that slide, but Bravo was pointing to the Milky Way super black hole. So a couple days afterwards, we ran this experiment, and I was fortunate that in all this time was going on, I had a computer science professor. I asked him, isn't there any way you can build me a simple data logger so I can take at least look at what's happening on the arms, so I can even see if why is one arm discharging differently than others? So I actually put these on 4 batteries on 3 of the arms, and so 3 of the arms had 4 batteries monitored, and it turned out that we actually were able to capture one of these outliers, the alpha arm, right here, showing us that something strange was going on. More typically, you would see this happen, where everything would sort of discharge more evenly. So again, now we're moving right up to today now. Like what's just been happening in the last week, and what happened in June and July when I had 2 students working with me, was whether we moved from just tracking pre and post voltage data for all the sensor batteries to having real-time data collection on all 8 arms. We haven't really graduated to having every single battery, so it's not 48 batteries here. We've got clusters of the 2 batteries, and we have clusters of the 4 batteries, so that's what we're measuring. 2 batteries all the way around, so there's 8 data points there coming in, and then the 4 batteries, set packs all the way around underneath them. So that's how we're covering the 6 batteries on every arm. So we don't have individual batteries, but we do have individual. We're sort of getting more sensitive as we go. And I think when you look at this data, it'll hopefully at least be mind-boggling. if you have an open mind, you'll at least say there's something interesting. Like, why would it happen to those arms in those orientations in a strange way? Why would it be there? And that's what we keep asking ourselves. So you guys are much more adept at this, but this was what we could afford. The exciting part for me is that the people in my university said, "Hey, sounds great. We're really glad you went to Advanced Propulsion Workshop last year." They didn't pay for it last year, but they are paying for it this year. So that's a real step in the right direction, And I was able to use my research overheads and things to buy some data sensors. This is some of the work that my students did. They actually said, which of these masses might we be interested in based on how big they are, what their distance is, and what their gravitational field potentially impact is here on Earth. So they gathered all this data and they were saying, whenever we see prominences of some of these big things, let's make sure we're testing that night, the middle of the night. The wonderful things of having students is they don't mind testing at 4 a.m. It's really hard for me to go and test at 4 a.m., but they say, "Hey, come on, there might be an event tonight. Let's test at 4 a.m. Well, that's a great idea. So let me know how it turns out. Let me know how it turns out. But anyway, so just before I flipped to their presentation, because I asked them, I said, look, create a presentation of the summary of your results. Because why? Because if this is real, and if it's fundamental, and it's that simple as I'm proposing, shouldn't undergraduate students be able to do it? And so I gave them the device, and they were funded by the university, they were funded by me, they were funded by the college. And I said, here's the challenge. Well, I'll let you see what they said in their slides. But I was very excited about this because, I'm all about these outliers, right? And when they told me, "Dr. Jansson, we're so excited, we got this 5 sigma hit." Yeah, I said, well, yes, great. Yeah, well, okay, so where was it? Was there anything near it? Was it something that you think could possibly be real? And they said, well, it happened right over here. And the interesting thing about this, we're using stellarium. The stellarium's what real astronomers use, right? Not the sky maps like me. I just use the sky map because I didn't know that you could use stellarium, which not only gives you everything that's in the sky in front of you, but gives you everything that's below you in the Earth. So the interesting thing about stellarium is you can see this north. This is basically where it shows the north, east, south, all this and west. That's the Earth. Okay, that's the Earth. But you just make the Earth invisible, and this is what's behind the Earth. Okay? So they were able to say, hey, look, we had this alignment of the moon and Mars and the black, well, it's not a perfect alignment of the black hole, but it's all there in the back, like sort of somewhat in the middle of the Earth. Well, wouldn't you know that that's exactly where the detector had its hits. So let me just go to this other presentation, which is the one that Peter put together. And if Peter was here and wasn't in the middle classes right now, he would be giving this to you. He's a rising sophomore, so he's a sophomore this year. He did this work over the summer as a freshman, intern. And Spencer is a rising junior. And so this is the results, and I'll just sort of share them as they gave them to me. I mean, obviously, I did correct typos, and I went back and made sure that the data that they pulled from the data files was correct. But other than that, this is pretty much what they had to say. So this is what they said. Research can be defined by completely disparate definitions, and all of them turn out to be correct. For our purposes, we'll define research as the following. It's the investigation of a theory or hypothesis through conducting tests that evaluate the material of interest under the conditions or constraints given by the theory. A successful research program is one that is able to prove or disprove initial hypothesis by creating objective experimental data. Otherwise, the research isn't finished yet. The researcher should be able to envision how the results should or could appear in accordance with the hypothesis or theory state, as the theory states. I'm not saying that that's a perfect definition of research, but this is what they believe research is. Okay, so this is how they're approaching their research. And they said this is what their challenge was. Dr. Jansson's work on the detector suggests that a force or some electromagnetic interaction of an unknown origin or nature may be affecting the voltages of batteries in this MFD array. And that these disturbances happen to be pointing in the direction of local celestial mass alignments. And heretofore undefined, a Machian EM inertial interaction may be the cause. So, here's the results. Get right to the point, okay? They spent the whole summer. I should actually have put a slide together to show you all the work they did, because it included taking a look at all 100 and so experiments that have been done before, doing statistical analysis on that. They put in the data logger, they put in the data system, they managed it, and they were doing all these things to refine the protocol, to get everything to work, but at the same time they said, well, we just want to run experiments, we just want to run experiments, we got to get this done by June, by July, because there's some major alignments coming up. They put a massive chart together of all the alignments that are going to be coming up for the next year, so all the times where we definitely need to be doing experiments. So the interesting thing was they had a number of voltage delta values with greater than 3 standard deviations from the mean. 7 out of their 18 experiments. They think their first 3 or 4 experiments may have been rubbish because they didn't quite have all the things worked out of the system. The other thing they did was impedance matching in terms of looking at all the impedance of the arms. They totally rewired all the arms on the device to put in as low impedance wires as they could to try to do the best matching they could. This naturally should have been, so basically said there were these hits in the massive interest had a percentage of about 85%. And again, they were never looking at more than 2 arms. So like they would go in tonight and say, these are the 2 arms that we should be, so they were almost to the point where it's like scientific hypothesis and testing. These are the 2 arms that should be impacted or impacted. So there's a 25% chance just by total randomness that they would get a positive hit. But here they had 85%. And of the ones that they experienced that were greater than 4 standard deviations of the mean, which were 3, which is pretty significant, because I've been hunting for a long time. And they actually found 3, and again, 100% of those actually pointed directly to a mass. And we define a hit as an electromagnetic interaction in some way, either internally through current drain or through externally through some field effect. The battery voltage is extraordinary in some way. That's what we mean by a hit. Because we don't know what this is. That's why we're presenting it to you, okay? We're presenting it to you because we think there's something real going on here. This one doesn't actually show you the where the center of the Milky Way is, because this slide was put in late, but again, the black hole in the center of the Milky Way is right around there. So here we have that outlier that you saw before when Mars and Moon aligned in the middle of the Earth and the black hole was there, but this was what I wanted to show you. We actually have this data that says all these batteries are draining. They should all drain fairly similarly because they're all powering the same motors and they're all in parallel. And since they're all in parallel and they have very similar impedances, they should all drain. And I'll show you some experiments that, you know, at the inspiration of Martin, we did with just the light bulbs. And sure enough, you look at it and you see that the batteries all do drain very much the same when they're running a resistive load. But something's going on here. And it's very, very strange what's going on here, because I can't explain why it does this. In the next slide I show you will even be more strange. But here you basically have this arm comes down. It looks like it's starting up here, comes down like this, and then boom, it just falls right off and recovers a lot lower. And that was the, we were looking at the bottom 4 arrays there. But this one that hits, the echo, that echo arm, is the one that's facing straight down to that prominence that was on the other side of the Earth. Coincidence? Well, you get so many coincidences after coincidences and you don't get false positives, and all of a sudden you say, no, this may be real. This may be something that's really real. Here's another one, July 15th. This was a, yeah, let me explain this to you too. You see this 4.8 to 6.8 sigma. So if this is just a normal distribution, this is out here at 4.8 sigma, okay? If this is your normal distribution, then it's out there at 6.8 sigma. So it's obviously an errant reading, okay? I mean, it's something you wouldn't have expected in your normal breakdown of these batteries. Whether these are normal or not, some of us have said, you know, they may be skewed in a certain way in pattern. That's very possible. I have a guy, Bucknell, who said when we finally get enough of this data, he's going to look at it for, you know, its real distribution. But it's going to be hard to figure out exactly what kind of distribution that is. But that was about a 5 sigma swing there. So something that we should be interested in if we're scientists. That's just my personal opinion. If we're scientists, we should be interested in that, because that may be as real as a gravity wave. It may be as real as a gravity wave. Now, I'm not going to comment on gravity waves because that's not my area of expertise, but this is sort of experimenting is sort of becoming a little bit more exciting for me. So basically, when the Sun, Moon, and Venus were basically on this arm of the detector, And alpha was basically, you can't hardly see it in here, but alpha's right straight up. It was basically where the Virgo supercluster was. Gulf pointed to Gulf pointed over to here, and hotel, and then alpha was there. So this happened to be out on Gulf. I can't explain this. I especially can't explain this in light of, the work that I see in the controls, actually what I would call the good controls that, was the folks from Dresden suggested as better controls for a device like this. Why is that one deviating? Why is that one deviating like that? So this is my students' work, okay? This is the other thing that I thought was pretty cool, right? Because when you yourself have been working on something for 18 years, you can start to feel like, well, maybe I'm just looking for something that's not really there. And so for me, it was very exciting when we got the funding of these students to just say, go test the hypothesis, work on your own. Call me when you can't get it to work, or you need some help. But this is your summer research project. So this is what they said. Overall, we observed 7 low probability outlier events in our 18 experiments. Also, the arms which were affected that experienced these strange drainage were pointing to mass alignments. In 6 of these 7 events, only one 3 sigma outlier case didn't point to an obvious target mass. From the experiments we conducted, it seems we are hitting our targets on a more frequent basis than before. Well, now that we have real-time data, it helps a lot. This is probably due to the rebound calculations which are being done now after every experiment, because they measure all the batteries, and then they go back and measure the first set of batteries so they can get a rebound curve that they can apply to all the data to try to get all the variation and results out. And he says our work is pointing in a promising area. And this is their last slide, and then I'll go back to my slides, and I only have a few more because I want to go through some exciting results of doing the Dresden kind of experiments. Could be battery failure, wiring issues, data log or systematic error, bad connections, or human error. This is what they said. This could be. However, the interesting fact is that whenever we have these significant impacts, it occurs on one of the 2 arms of interest, either the arm that's directly going down through the Earth or up to the reaction body, or the potential source of what's providing that. So, and again, this is our greater than 4 sigma variances. So let me just run back to the final few slides here, if you just bear with me a minute. And we'll hopefully get done on time. One of the interesting things to me, because I postulated this a year or so ago, and I don't know if you guys sort of picked up on it, but I said, wouldn't it be strange if it was just there in plain sight all the time? But since we're not really looking for it, we're not really expecting it, we don't have any theory that would explain why you would be looking for it. It just seems to be covered up in just the natural variation. Well, if you look at how many times you would expect to get an Earth hit on this device, from just total chance, it's 3 out of the 8 arms facing down. So 3/8 is 37.5. The actual data from the experiments was 36.79 for 110, 120 experiments. It's basically saying what you would randomly expect to happen is actually what this shows. But during certain times of the year, when you get these special prominences, then the thing didn't blow that out of the water. But on those other times of the year, it gets a lot lower than you would have expected. But when you're done, you get random probability. But it's not random. It's made up of all this, interactions of all the matter in the universe, all pulling in different directions. But at the same time, the local matter matters. And I think, Jose, you even said that in your talk, that local matter may matter. I don't want to put words in your mouth, but I'm just saying local and the macro and the micro may have an impact. So that was interesting to me, that those numbers just happen to be almost identical. So let me get to the TU Dresden supportive comment, which was, why don't you just run lamps? Just try to run lamps. And that to me was a really, really, really good idea. We haven't run enough lamp experiments yet. I'll say that. We only have 8 experiments done so far because we've been doing them. The students they were most excited to try to see if they could get hits. And I said, come on, you got to run lamp experiments. We really got to see what the lamps are doing. And I don't know, maybe it's my imagination, but when you look at these discharges, they look a little more like you would expect from parallel arms. They're all connected to the same load. They sort of, I mean, there's variance in here. I mean, the scale's pretty small here, I know, from a few volts down to a few volts and then rebound. But what was really, really, really interesting to me is when I took what I call the Dresden incandescent lamp experiments and looked at the few of those that we have, and I'm obviously going to create that, turn that into 40 or 50 experiments as the students get time to help me with that. The change in the mean suggests that we were draining about the same amount of energy. I mean, that was our intent. Our intent was you want these lamps to be loaded the same way the motors are loading the internal gyro. Because you don't want to say, well, I underloaded it or I overloaded it. And then so it was pretty close that we drained the same. It's not identical, but we have to work on refining that. Maybe put in another lamp in parallel or whatever. Standard deviation was about 6, and the range was about 30. So if you just run incandescent batteries, now obviously, there's other factors that come in play when you're all of a sudden you're going to use that same amount of energy to drive motors, because the motors are spinning a mass now, and that mass is going to be inside your battery array. So yeah, there probably is going to be some sort of other electromagnetic effect, and we see that. We see that there's a 10 millivolt standard deviation. It starts to spread out. The range is getting bigger, 70 millivolts. And then when you look at what I call the experiments, where you actually compare these controls, means you spin the gyro up, but you just keep it spinning. The experiment is you spin that gyro up, get it spinning, and then you torque it. You try to keep it turning when it's in its gyroscopic kind of effect. It doesn't want to turn, and now obviously you get a much bigger drain of the batteries. These are not the batteries that are providing the torque. Remember, these are not the batteries that are actually torquing it. These are the batteries that are just keeping it spinning. So there's some external force, obviously, putting a bigger drain on the battery when you try to torque it, and the standard deviation goes up, spreads out, and so does the range. So the next steps are obviously, we've got a lot of other experimental alignments coming up, and we're going to hopefully do it. I'd like to leave you with a couple quotes, because I do believe that this is true. This is written by a lot of people smarter than me, but to continue the progress of science, we have to, again, confront the deep questions about space and time, quantum theory and cosmology. The directions in which progress are being made are taking theory back into contact with experiment. And to me, I have to suggest to this group, because I know how open-minded and brilliant you are, there's got to be something going on here that's a little more real than my imagination. And gradually, a solid Machian law of inertia is emerging. While not yet recognized by the physics community at large, its universal stature is sure to win through in the 21st century. The force of inertia is a signpost to new knowledge. And I actually believe that that's true in the laws that demonstrate it. And we may not agree with instantaneous action at a distance forces. I'm not a physicist, but a lot of you are. But I do believe that this is not coincidence anymore. I actually believe we're onto something. I'd like to thank these folks for helping build the thing. I'd like to thank all these people in Europe and in the United States that helped me, and Professor Woodward and Heidi for this great workshop, and all the folks from last propulsion workshop and the very first propulsion workshop that were kind enough to let me try to keep working on this. And Eric and I would like to thank the students from Bucknell that are working on it and have been working on it this summer, and the other folks in integrated systems. And then obviously we're very thankful, as we all are, for those who will fund us potentially in the future. Thank you very much. Thanks.